capacitor, the top one, number 1, or chased off this, would migrate and go out this direction. And so these would come out, and then these would come out. So again, that's what I mean by these parallel lanes. This would be Santa Barbara, this would be CARP. Some of the cars would go this lane, this would be the fast lane. Some of them would go this one, that's the slow one. And the behavior is a little bit different. And so when we want different things to happen, we will hook them up different ways. Series versus parallel. All right, so we are essentially asked in number 3 the same thing we were asked in number 2, and that is, what is the equivalent capacitor from a calculation, and what is the equivalent from a measured value? And let's try both of those, and if they agree with each other, then we must be doing things right. That is, the theory must be right, and our calculations must be right, and our connections must be right, and we must be using the meter right. Now, this will give me a chance to say, go back to the lecture, and you'll see me derive that the equation for the two capacitors in parallel is just the sum of the two. So it's a little easier calculation than the reciprocal sum. So reciprocal sums, sometimes referred to as harmonic sums, are a little bit harder because you got to do reciprocals, and then when you get the answer, you got once you add them together, you then got to take the reciprocal of that. Where this is just straight add them together. So I won't actually do this calculation, and hopefully I'll stick to it this time. I know I said that on the other one, but I'm going to let you do these two calculations. And so this first one is the 0.981 microfarads, and the other one is the 0.484 microfarads. And so just add those together. I trust that won't be a trouble for you. But let's see if it agrees with the measured value. So let me come over here and grab our capacitors. In fact, I'll come back over here where you can see me a little bit better on the video recording. And let's rehook this. And I like to tell students this. And so when your day comes and you get a chance to actually be in the classroom again and use the meters, I always like to say, disconnect the meter and put it aside. The meter is a measuring device, and when you're working with your circuits, it's going to be what you hook up last, right? Let's just make sure the circuit's right. This can just confuse us, and so I like to just move it aside and say, let's hook up the electronics first. Then we'll hook up the meter. So if I were to hold these, and maybe I'll just connect the one that was the series for just a second, but I'll also grab another wire getting ready. I might actually hold it in my hand so that it kind of looks like this. Maybe I'll hold it this way so I've got the bigger one on top as my picture shows. So there is the 1 microfarad, and I would call this then the first plate of the first one, and this over here is the first plate of the second one. And so this is saying connect them together so that if you did hook a power supply, the electrons can go either to this one or to that one. And then likewise, this would be what I would need to connect the second plate of the two capacitors together. And so hopefully then what I hold in my hand looks a little bit like I'm drawing up here to kind of give us that intuition of what to do. And so I've hooked the first plate of the two together, and I've hooked the second plate of the two together. So if I've done this right, I've got these in parallel. Now I just need to hook up my meter to measure these equivalent. Or if there was a power supply, it would be getting its the electrons and the charge would be building up. All right, so in the picture it looks like I'm supposed to plug it into the wire in the middle here, and I don't have a connection for that. But remember that a wire is what we said is an equipotential in chapter 25. And so it really doesn't matter where you connect the wire to. So I'm going to connect it to here. It would work just as well if I connected it there. But as long as it's connected to this wire, it is also connected to the first plate of the two of them. And so the other connection is going to go here to this wire. Again, doesn't matter where, just somewhere on the wire. Like I said in my picture, I drew it like the middle so you can understand it a little better, but I don't have that option on the wire, and I don't really need it. And I get a number of 1.465. So 1.465. And I should put my units here, microfarads. Okay? And so that's the value of those two. So again, do this calculation and see if those two agree. Because like I said, if not, we should stop and keep doing it until they agree. But in this kind of weird remote setting, we can't really do that. But that's the intent here. Let's move on to the hardest of this first half of the lab, number 4. Number 4 is a combination of series and parallel. Watch this. It says, connect the 1 and the half microfarad capacitors in parallel with each other, and then this results in series with the 0.47. All right, so if I read that right, they said connect the 1 microfarad and the 1/2 a microfarad in parallel and that results in series with the 0.47. And so I kind of described that with 2 different connections, but I'll just finish it off with that and then put in a little circle there. And they're saying, say now with these 3, make your hookup. So let me call this C1. Let me call this C2. Let me call this C3. And like we've done on step 2 and step 3, let's both measure it and calculate it. And since I'm doing measurement, let me do that first. So I'm going to say, all right, let's take the equivalents as measured and see what I get. All right, so here's where I would say it's a little more complicated. I will start by the same thing I said before. I think the best technique I can kind of teach you is as you're learning this stuff, hook up the meter last. As you get more experience, maybe that won't be necessary. And sometimes it makes sense just to tear everything apart and start anew. But as you gain experience, you might realize maybe there's something in the past one that is connected to the new one that I don't need to take all the way apart. And in this case, that is true. You can see that these 2 in parallel is exactly what we were just asked to do in number 3. So I'm going to begin this last circuit here with saying that these are already done. This right here would be this connection. This would be the first plate of these 2, okay? And this right here would be the second plate. And what they're saying then is take this and send it to this capacitor. All right, well, that means if I were to grab another wire here, I would say connect this one right here to this 0.47. Now here's where it can get kind of weird looking. I wish I had the 0.47 over here. It would look prettier. But where is that 0.47? If you remember, it's right here. So you kind of have to imagine me taking this 0.47 and maybe sliding it over to here, because I would take this and plug it into the first plates of this third capacitor, and that's going to be right there. So that's the first plate, and then that would be the ending point. And so this point right here would be that one. And of course, as we already mentioned, this right here was this connecting wire for the first plate of capacitor 1 and capacitor 2. And so it makes this measurement a little tricky for those who are in the lab doing this for the first time is, ooh, where do I put my meter? And so your meter is from the beginning to the end of the whole equivalency of those three. So in this case, it would look something like this. The first wire on my capacitor meter would be right here, which would be where the first plate of capacitors 1 and 2 are connected. My other wire on my capacitance meter would go to the second plate of this third capacitor. And I get an equivalent of 0.350. So I'll write that down for you. 0.350 microfarads. Now, a little challenging then for you is how do you calculate the equivalence? And this is where you'll have to do a two-step calculation, because maybe it's best to then think about this as this being the equivalent of capacitors 1 and 2, then hooked in series with capacitor 3. Oh, crazy post is in your way? Maybe I'll draw it again here then. All right, so this equivalence of 1 and 2, and then number 3. Okay, so I'll help you a little bit here, but remind yourself that this equivalent is in parallel. And back here we talked about it, as well as in the lecture, that you can get the equivalent in parallel by adding them together. So you're going to add these together, although please remember, you're not adding the 1 and the 1/2. You're adding these two numbers. And you really already did that in step 3, and that's kind of my hint towards you. So you could take what you just did here back in number 3, this value, that is what I would put right here. So then I could say that the equivalent of all 3 of them, 1, 2, and 3, since these are in series, would be, and so that would be the reciprocal of the equivalence of 1 and 2 added to the reciprocal of number 3. See, that's the series calculation. And that's what I did just to remind you back here in number 2. In fact, maybe now you can kind of see and the game we're going to play, because I suspect you might be trying this lab maybe before you've done too many of the homework problems. But the homework problems will start giving you a really complicated circuit. I mean, they'll start off with easy ones, like 2 that are in parallel. Okay. But then they'll put 3 that's a combination of series and parallel, like we're doing now. And so this is how you would do it. But then they'll give you 4 or 5, and I think one of them will even have 7 capacitors. I might be mixing it with another class. But to get the equivalent of those 7 capacitors, you've got a number of steps you have to take. And so the problem can get much more complicated than we're seeing here in the lab. And the lab is, just kind of this mediate step. And so we got series parallel, and now we have combinations of the 2. All right, well, I will say that's the first half of the lab. Let me clear off the board so that I can then kind of repeat everything. I'm sorry, not repeat, but rewrite over all of this, because the other half of this lab is the part that I was saying was the first half of the lecture. What is a capacitor? How do you actually build it? And then, of course, what factors affect this capacitor? And so instead of using these commercially bought capacitors, we're just going to take some metal plates and build our own. Hopefully with the idea that you'll have a fuller understanding of what these things are all about. And so hopefully we're getting together the physics of what's going on and then the applied physics or the engineering of what's going on here. All right, so off to number 5, and I won't write anything on the board quite yet. Let's read the question. 5 says, build a parallel plate capacitor with an air dielectric. Now, the parallel plate means that you have two pieces of metal that are parallel to each other. And as I was showing you earlier, I have a metal plate right here. It's got a little handle so I can hold it. Okay, so here's I'll call this my top plate. And I can connect a wire to it. I won't yet. And then this one's on a nice little stand, so I can just kind of play with it. But you can see here is the metal plate. And so that's the bottom one. And all they want me to do is to kind of make them parallel like that. That would be a parallel plate capacitor. However, they say, and listen to these words carefully, with air as the dielectric. Now again, assuming you've gone through the lecture, the dielectric is the material that is between the two plates. And obviously, the stuff between the two plates has to be an insulator. Because if it was a conductor, the negatives on one plate would just move over to the other plate. So the dielectric is a insulator, and in this case we'll just use air. But to make things as accurately as possible, I'm going to do this. And I hope this doesn't confuse you. I got 3 pieces of plastic. They're little tiny, tiny pieces. Now I'm going to use them as spacers. I'm not really filling the space between the plate with the plastic. Do you see how when I put this on here like this, they are now spaced apart by the thickness of that piece of plastic. But most of the space in there is air. I know there's a little bit of plastic, but most of it is air. And so that's how I'm going to build a parallel plate capacitor, making sure it's parallel by using the same size spacer. If I tried to hold it with my hand, it wouldn't work well. Okay? And so I'm just going to say this is air filled. I know. I'm going to keep saying it. I know there's a little bit of plastic in there, but that's minor compared to the most of it. All right. So calling the whole thing an air-filled capacitor, I would say I have just now built a parallel plate air-filled capacitor as they're asking for in step 5. And that's where they say here, you know, separate the plates with 3 small plastic insulating materials. Okay. And then it says, go ahead and measure and calculate what this should be and see if they're close. And if they're close, move on. They even say, and I think the other ones did too, calculate the percent difference. I usually tell the students not worry about that and skip that. And I'll say it here too. I'm not so much we're interested in the calculation of the percent difference for these as much as do they agree with each other? Because my common phrase is, hey, if they agree with each other, you're doing it right, you're understanding, move on to the next step. And that's the idea. And so you may not do it right the first time. So let's go ahead and both measure and calculate this. I'll start with the measure since I'm here. I already hooked it up, and I've got my meter right here. Now, in this case, I'll just grab my capacitance meter here. And these guys all move out of the way. I think we're done with those for the lab. And because those are the commercial ones. So the homemade one, I can connect to the bottom plate, and I can connect to the top plate. And I will tell you that the capacitance here is really, really small. So holding up my capacitance meter again, you'll see that I got a really, really small number. It says 0, maybe 0.001. But remember, this dial is designed so that you could go to more accurate settings as long as you don't go above that. And if I keep looking at this, I will see that the best setting for this one is actually the lowest setting. The lowest setting reads in puffs or picofarads. Puffs a kind of a slang for picofarad. So forgive me if I accidentally use the word puff but it's picofarads. And remember, pico is 10 to the minus 12. All right. So this says it can read up to 200 picofarads. And this is a little bit under that. This is reading 146.5. So putting some numbers so you can write it down, I'll say, okay, here is number 5. The capacitance that I measure for this homemade capacitor is 146.5 picofarads. Puffs. Okay, little tiny ones. And so small capacitance. Now, the other part of this problem says go ahead and calculate what it should be. All right, well, another reason why it was important for you to see the lecture on this is we derive, or the book also derives if you're in the book, that for a parallel plate capacitor, the capacitor is the permittivity of free space, if it is free space between the plates. And in our case, we have air, which, with a little bit of plastic, okay. But for the most part, it's air. And even air is mostly just free space. And so we're going to say that I essentially have nothing between the plates. I know I have some air molecules there, which I guess is mostly nitrogen molecules. But that has a small effect. So we're just going to, in our calculation, assume that it's the same. And so our calculation won't match this directly. In fact, maybe I'll actually do a calculation on this one here with you, because there is something that you should probably see. But the A is for the area of the plates, and the D is for the distance between the plates. Okay. So my plates are a circle, and the area of a circle is pi r squared. And so here is pi. We need to measure then this radius, and I'll just confirm, but I've done it so many times over the years that I know it's 7.5 centimeters. I'll just do the whole diameter. Yeah, so the whole diameter is 15 centimeters. So half of that is 7.5 centimeters. So I will put in 0.075 meters and square that. So there's going to be the area. And the distance between them is the thickness of that. And I'll measure those too. But again, I've done this quite a few times over the years. So I'm sure it's the 1.25 millimeters. In fact, I'll just use the piece of plastic out of here. They're all off kind of the same sheet, the same thickness. And so I'll just cut it. Yep. 1.26 instead of 2.5. But 1.26 millimeters is what my calipers say. So that's the spacing between them. So 0.00126 meters. So if I go ahead and grab my calculator, this would be 8.85 times 10 to the minus 12. And I remember doing this a bunch of times the other night and the night before. I made a bunch of solutions with this. But remember, this is Newton meters squared, coulombs squared for the units of the permittivity of free space. The area, as we are about to put into our calculator, would be in square meters. And the distance, 0.00126 meters. And so let's see what we get. And let me save some space over here. So I'm going to put this down here. But I wanted to take a moment to look at the units. And so meters would cancel with meters. That's going to go away. And maybe it's worth pausing that, remember, capacitance is measured in farads. And our definition of a capacitance was how much charge do you get per volt. So the units of a farad would be a coulomb per a volt. Okay. Now, if you also remember, a volt is an energy per charge, so that's a joule per coulomb. Now, watch this. At the bottom here, I will take the Newton and the meter and put them together to call that a joule. In the top, I have coulombs squared. I will leave one up there, but take the other one and move it to the bottom, the denominator of the denominator, an improper fraction. And that's a volt. So I'll just go volt. So that is a coulomb per volt. And so that's a farad. All right, so now let's get my calculator, because this does differ by a significant amount that can confuse you. And so I want to make sure I do this one here. So let's see what I get. And so I will go the 8.85 times 10 to the negative 12 for here, times a pi, times a 0.075 squared, then divided by a 0.00126. Got it stuck in my head, but I actually measured a 6 this time. And I come up with 124. 24. I rounded it up. It doesn't round up. It stays 24. Okay. 124 times 10 to the negative 10th. Which, so I can compare it to the measured value, I'll write that in pico. So this would be 124. Move the decimal this way, makes that bigger, makes that smaller. That becomes minus 12, so that's a picofarad. So 124 puffs here, picofarads. And that is why I wanted to do the calculation. There's nothing wrong here. I know this is a little bit, maybe even quite a bit lower than that. And this is usually in a face-to-face setting. I walk around and people get this number, and I said that's okay. What you calculate is a little bit lower, and here's why. Our capacitor has this metal plate that's got a thickness and a gap that has a thickness, and our equation from class is a little too idealistic. This is how we calculated in class, that there would be a charge of pluses and minuses on the two plates that would build up. But what happens with our capacitor is we get charge building up on the thickness of it, the sidewalls. And so not only do we have an electric field between them and a charge build up between them like this, which is accounted for with this idealized equation, but we get a little more capacitance than anticipated, because we have, in addition to the parallel plates, we have what we call the perpendicular plates of the capacitance. And so it adds another 16% or so. And so we get a number roughly about 16% lower than that, about 1/6 lower. So anyways, that's what I wanted to point out, and make sure I did that calculation so you weren't too worried that you were doing something wrong here. You will get a number lower by about 16%. We get these little sidewalls here really add up. Okay. In fact, maybe I'm getting kind of ahead of our understanding, but if you can see this on video, this might be a good time just to kind of point out. Right now, the capacitance is this 146 I've been talking about, and of course that's the parallel plate and even the sides of it. But if I were to touch it, this would put charges on me. And so watch what happens when I touch it. It goes up. Looks like it goes to 153. So it changes the capacitance. And so charges flow around. And this is why I'm pointing it out. How do you think the touch screen works? It knows where you touch. There's little tiny capacitors there. If I were to touch that one, boom, it knows where I touched it. The capacitance changes and the charges flow on and off. And so I become the conductor. I'm touching it. And so these 5 layers on your touch screens play an important role. And one of those is the capacitance of it. And anyway, so that's kind of where modern technology has evolved to these touch screens, and they're all based on the capacitance and then using a human. That's why, I don't know if this has ever happened to you, it certainly hasn't been cold around here, but in wintertime it can get cold, and I have spent many times watching my kids play soccer in the stands at the high school, freezing cold, and I'll have a glove on or two, and I can't use the phone, and because you can't touch it, and so it's annoying. And anyways, we're past that stage, and in fact, all their soccer stuff has been postponed. So I guess I don't have that problem. I've got actually the opposite problem now. Now my phone won't unlock because I got my mask on all the time, and so I go into the store and I try to pay something on with my phone, and it won't unlock because it can't recognize my phone. So not a big deal. I just got to do the passcode, but it's kind of a pain. But not the biggest pain is catching the coronavirus, so I keep my mask on here. All right. So anyways, I digress, and I better keep going because this is a long one. And step 7 is a really long problem in here, and so we haven't even got to that. All right. So let's go on to step 6. And as I said, step 6 is like 5 and 6, is to really kind of understand this equation. And step 6 is saying change this. Change the distance between the plates. Because this is saying that the capacitance should depend upon distance. And it should be an inverse relationship. And so that's what we're going to do in step 6. And by the way, in step 7, we're going to change the area. I'll get to that one. That's the hardest one of all here. But step 6 then, if you're looking, has this. You are to make a graph of how does the capacitance change with distance. And we have these spacers, and if you'll see it, it says 1 spacer, 2 spacers, 3 spacers, 4 spacers, 5 spacers, and 6 spacers. And what they're talking about is what I was showing you earlier. They're talking about this. They're talking about stacking these plastic pieces and their thickness up. So right now, I have just one set of spacers in there. That's how we set up number 5. And so I would say the distance is 0.00126. And so this would be the distance in meters, and this is the capacitance in picofarads. What was it? 146.5. And so that first one's already done. But let's move on to the second one. So let me take this apart. So I'm going to lift this off. And I'm going to put another piece of plastic on top of the other ones. And so now I have doubled that distance. So 2 times this number would be, what? That would be 24, 25. And so that is the spacing now. And the capacitance I get is 78.4. And so that's the capacitance. And let me do it a few more times here, and we will hopefully see, as the equation predicts, that as the distance keeps getting bigger, the capacitance keeps going down. All right, so I'll try 3 plastic pieces in here. All right, so let's stack 3 high. And if you stack it 3 high, I get 50, where is it going to stop? 54.9. So 54.9. Times 3 here is what? An 8, a 7, a 3, and a 0, 0. Actually, maybe I'll stop doing that. I'll let you do the thickness of it. But let me continue to get the values of the capacitance so that, of course, you can eventually also make a plot of this and see that it does follow the pattern. And so now we will be, well, that's a paper one. That should be over there. Well, it looks like these are all messed up. So did I put one here? There's 4. Now I lost track. 1, 2, 3, 4. 1, 2, 3, 4. And this was the one.